Good morning, everyone. Today we are doing Unit 2, Lesson 3, Graphs of Polynomial Functions. So before we jump into the graphs of polynomial functions, we're just first going to look at what makes a polynomial function a function in terms of its equation. So you can see here a polynomial function is a function whose equation is in the form y equals a subscript n x superscript n plus, and then it's a n minus 1 x to the power of n minus 1, and then plus a n minus 2, x to the power of n minus 2, and so on and so on. So it's basically saying that this is the first term, right, is to some number n, and then we put them in descending order all the way down to 0. So if n was 5, for example, then the next one where it says n minus 1, this would be x to the power of 4, this would be x to the power of 3, and then 2, 1, 0, all the way down in descending order. But there's a couple of things we need to know about the characteristics of this equation as well. So the exponents, n, n minus 1, n minus 2, they're all whole numbers. So exponents are whole numbers. The variable is represented by x, or any other variable, and the coefficients are real numbers. Okay, so coefficients don't have to be whole numbers, but they do have to be real numbers. Okay, so if we wanted to list some examples of polynomial equations or polynomial functions, we talked about that a line is a polynomial function, so we'll write that as a yes example. We know that a quadratic, from the notes earlier in this unit, are also a polynomial function. And then we can have a function with a degree that's higher than a quadratic, say to the power of 4, which we're going to look at. These are called quartics, so we're going to look at these functions too with a higher degree like that. Some examples that would not be polynomial functions. Okay, we can't have a square root in our polynomial function because this is really an exponent that's a fraction, so it's not a whole number exponent. We can't have a negative exponent. So if we had something like 5x to the negative 2 plus 1, we can't have that as a polynomial. And we also can't have a fraction that doesn't simplify to just a whole number, because when we try to simplify this, this is really 3x to the negative 1. So we could rewrite this as f of x equals 8x plus 7, and we could say that it was times 3x to the negative 1. So again, you have that negative exponent that you can't have in order for it to be a polynomial function. Okay, so those are just some characteristics of the equation of a polynomial. So if we want to talk about the characteristics before we start looking at the graphs, let's recall what domain is. Domain is the set of x values. So all the possible x values for that polynomial function, or our input values, we would say, that exist within a function. Our range is our y values, or our output values that exist within a function. And then the way we write, we use function notation. So we put the curly brackets, and then we'd say x for all real numbers. So this would be read as x for all real numbers. And sometimes there might be some restrictions on the domain, saying like x for all real numbers such that x is greater than or equal to 0, or whatever the criteria is for that function. So for range, same thing. This has a restriction though. So this shows that y, the range is y for all real numbers such that y is greater than or equal to 0. So y is all real numbers that are greater than or equal to 0 is basically what that's saying. Okay, some other characteristics. The degree of a polynomial function is just the highest exponent of the independent variable, which is our x variable. the leading coefficient is the coefficient, or the number, of the first term in a polynomial when the terms are written in descending order by degree. So it's the coefficient on the variable with the highest exponent. So when we were talking about the degree, whatever coefficient is on that variable that has the highest exponent on it is our leading coefficient. Okay, our end behavior. Our end behavior is what happens to the y value as x approaches positive infinity. And how we write this mathematically is we say x, and then we draw an arrow pointing to the right, which means approaches, and then we would write our positive sign, and then our infinity sign, which is a sideways 8. So I just want to write that this arrow means approaches. So x approaches negative infinity, or positive infinity, sorry. And as it approaches negative infinity, we'd say x approaches and then negative infinity at the end of the function. So we summarize the end behavior in this manner. So we would say as x approaches negative infinity, because that will be on the left bound of our graph, then y is going to approach a positive or negative infinity. And we would say as x approaches a positive infinity, then y approaches positive or negative infinity. And we'll look at some graphs to show exactly what I mean by that. So let's first look at a linear and quadratic functions and see if we can describe all those characteristics of a polynomial we just talked about. So for our domain, we're looking at all of our x values. So remember that a line continues on forever, right? So this line will continue on positive x forever and ever, and on for a negative x forever and ever on the left side. So we would say that the domain is x for all real numbers. The same is true about our y value. As our line continues to increase, our y values are going up, and as our line decreases on the left side, our y values are going down. So we would say that we will have all of our y values here as well, so y for all real numbers as well. The degree of this function is what is the highest exponent on my x variable. So if there's nothing there, it's implied that there's a 1 on that, so we would say that the degree is 1. And what's the sign of that leading coefficient? So my leading coefficient is what's the number on my variable with the highest exponent. In this case, is just an exponent of 1. So we have a positive 1, or a positive leading coefficient. Our end behavior. So let's look at our end behavior for a line and talk about those infinity ideas. So as x is getting more negative on my graph, what's happening to my y's? So you can see here that if we look at my graph in terms of moving more negative, so as my line moves more negative on my x, what's happening to my y? Well, my y is also getting more negative. So we would say as x approaches negative infinity, y approaches negative infinity. Okay, and then we can take a look at what's happening as x is approaching positive infinity. So as x is getting more positive, right, or moving higher up in our positives, what's happening to our y's? Well, our y's are also getting more positive, or approaching a positive infinity. So let's write that. So as x approaches positive infinity, y approaches a positive infinity. And then is this relation a function? So if we could draw that vertical line anywhere on the graph, is it only going to cross it once? Yes, it is. So we'll say yes, it passes the vertical line test. Okay. Each input has one output, only one output. Okay, the next one we're going to look at is quadratics. So for a quadratic, what is our domain? Well, in this case, our x values, again, they continue on the left in the negative, and they continue on the right in the negative, and this graph is going to continue on indefinitely on both sides. So eventually we're going to hit all those x values. So we'll say x for all real numbers. Now our y, we have to take a look at, are we going to hit all of our y values? Well, the graph starts up high and then comes down and makes a turning point at my vertex. My vertex is here at 0, -4. Okay, and then it heads back up. So my y values are never going to reach below that -4. So we'll say y for all real numbers such that y is greater than or equal to a -4. All right, the degree. So what is the highest exponent on my x? Is going to be a 2. So degree of 2. And the leading coefficient on that is a 1, and it's a positive 1. So again, it's positive. So what is the fact that it's positive and then it's a degree of 2 tell us about the end behavior? So again, our end behavior, as x is getting more negative, well, in this case, my y is getting more positive as x gets more negative. And as x is getting more positive or moving towards positive infinity, my y is still getting more positive or moving towards positive infinity. So we would say, as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y is still approaching positive infinity. So no matter what, y is getting more positive either way you look on that graph, which makes sense because we can see both of our endpoints are moving upward in a positive direction. Is this relation a function? And again, we can say yes. It passes the vertical line test. So we're now going to explore looking at some other functions, and we're going to look at them on Desmos, which is just an online graphing calculator, and see if we notice any patterns with different types of functions. In particular, we're going to start by looking at functions with an even degree. So you can see in my first equation, it has a degree of 2. So we've learned in previous math classes that a degree of 2 is a quadratic. Right, the highest degree on that function is 2. So that degree of 2 is what we call a quadratic. This function, the highest degree is 4, and this type of function is called a quartic. Think quarter, right, 1/4, so anything with a degree of 4 is called a quartic. So we're going to explore even degree functions on Desmos. So I'm going to pull that up for everyone to see. So if I go to my browser, and I hit Desmos, you'll see that where your mouse is in this number 1 line, and I'm just going to move it up so that we can see our table. And then in this line you can type in an equation. So if we type in our first equation, which is y equals 0.5x squared, so you hit that a to the power of 2 button to get the squared, minus 3x plus 1. Okay, we can play around with Desmos. Okay, we can scroll in and we can scroll out. You can change the x and y axis scale if you need to see more of the graph, if it reaches up higher or lower on the graph. So it's something to play around with, which I'm sure you've seen in other math courses. But let's describe some of the characteristics of this graph. So first of all, the sign of the leading coefficient. So my leading coefficient is 0.5. It's the number that's on my highest degree x value. So x squared has a 0.5 on it. So the sign of my leading coefficient is positive. And if we look at the end behavior again, as end behavior is approaching negative infinity, so as my x is getting more negative, what's happening to my y? My y is continuing to get more positive or approach a positive infinity. As x approaches a positive infinity, y is continuing to get more positive, right? It's continuing to go up or approach a positive infinity, okay? Let's type in the next equation. So the next equation is y equals, and then this time we're going to do x to the power of 4. So we're going to hit this little a to the power of b button, and that'll put the mouse up so we can type in an exponent. And then we'll hit our over arrow so the mouse comes back down. Minus 2x to the power of 3 plus 2. Okay, so x to the power of 4 minus 2x to the power of 3 plus 2. So we can see, looking at this, that our leading coefficient, again, our leading coefficient on the x to the power of 4 is just a 1, and it's still positive. And similar to the last example, as x approaches negative infinity, y is still approaching a positive infinity, or getting more positive. And as x approaches a positive infinity, again, that endpoint y is getting more positive, or going up. Let's look at the next example, y equals negative 2x squared plus 3. So this time the graph is actually pointed down. We have a quadratic or a parabola that's pointed down. If we look at our coefficient, our leading coefficient is this minus 2, and it is negative, so that's the sign on our leading coefficient. As x approaches negative infinity, y is approaching a negative infinity. So as x is getting more negative, so is y. And as x is approaching a positive infinity, y is still approaching a negative infinity. So either way, y is always approaching a negative infinity, which makes sense because the endpoints are going down. Go ahead, pause the video, and try the last one on your own. So here's the last example all filled in. Again, we have a negative coefficient, and the end behaviors are approaching negative infinity, both when x is approaching negative infinity and when x is approaching a positive infinity. Okay, so those are the even degree functions. If we had a power of 2, a power of 4, and a power of 6 in this table. So we had a power of 2, a power of 4, a power of 2, and 6. So those are all even degrees. And hopefully, we're going to summarize, hopefully what you saw when we look at this is that when we had a positive leading coefficient, okay, when we had a positive, our end behaviors were positive. When we had a negative leading coefficient, both of our end behaviors were negative. So we're going to summarize that in another note. But let's look at the odd degree ones, okay? I'm going to pause the video and put the first example up on the screen. Okay, so we put up in Desmos y equals 2x minus 1. No surprise here. This is a degree of 1, so we just have a linear relation, or a line. All right, the sign of our leading coefficient, we have a positive 2, so we have a positive leading coefficient. And if we look at our line, as x approaches a negative infinity, so as x gets more negative, y is also getting more negative. It's continuing to go down, so y is approaching a negative infinity. As x approaches a positive infinity, in this case, y approaches a positive infinity, right? Y is continuing to increase as x does, so we would say y is approaching a positive infinity. The next example we have here, our degree is 3. Again, still an odd degree, but when we have a degree of 3, we call this a cubic function. So I'm going to pause the video. I'll put that one up on the screen. Okay, so our next example is y equals x to the power of 3, or x cubed, minus x. So that's what we have on the screen now on Desmo, and you can see that we still, again, we have a positive leading coefficient because we have a leading coefficient of 1, and it is positive. And then if we look at our end behavior, again, as x is getting negative, so is y. So y is approaching negative infinity. As x approaches positive infinity, or gets larger, y is also approaching a positive infinity. All right? So looks very similar to a linear one. When x is negative, y is negative. When x is positive, y is positive. Take a minute, pause, and try to do the last two on your own and fill out the table of values and put them in Desmos as you go. So here's the graph of our third function, y equals negative x cubed minus 2x squared plus 1. You can see that our leading coefficient is negative. And if we look at our endpoints, as x is getting more negative, y is getting more positive, or moving towards a positive infinity. And as x is getting more positive, or moving towards a positive infinity, y is then moving towards a negative infinity. All right, and if you plugged in that last function, you should get the same results with the negative leading coefficient and the same end behaviors as the previous example. So something to note here, which we will summarize as well, when we have a positive leading coefficient, then our y values start negative but then go positive. When we have a negative leading coefficient, our end behaviors start positive but then go negative. All right, so let's look at the rest of the note. So let's just summarize here what we saw when we used Desmos. So when we had an odd degree polynomial, so remember those odd degree polynomials were linear and cubic. right? A cubic, remember, is x to the power of 3, so that has an odd degree. If they were positive, then our end behavior was such that as x approaches a negative, y approaches a negative. And as x approaches a positive, then y approaches a positive. Okay, it's going to be similar to the graph of y equals x, which is just a line. So think about how a line can go up to the right if it's positive slope, or it can go down to the right if it's a negative slope. So if we have a negative degree or negative odd degree polynomial, as x approaches negative infinity, y is going to approach a positive infinity. And as x approaches a positive infinity, y is going to approach a negative infinity. So let's actually look at this. So if we were to draw a rough sketch of this, so if we were doing a cubic, for example, which we saw on the last page, a cubic looks something like this, a positive one. It's going to start as x is negative, then y is negative. And then it's going to go up and back down, and then finally up again. So that as x is getting more positive, y is getting more positive at the end of the graph, on the end behavior. So this follows, or is similar to a line. How a line to the left at the end of the line is getting more and more negative, and at that right side of it is getting more and more positive. So a cubic follows that same kind of idea. If we have a negative odd degree, so just think about kind of flipping this over the y-axis for a negative odd degree. So in this case, the graph is going to start as x is getting more negative, y is going to get more positive. And then it's going to come down, up, and around. And as x gets more positive, y is going to get more negative. So it's going to be like the mirrored version of the positive one. And this would also follow the pattern of a line with a negative slope, where a line goes down from left to right. So if we look at the domain of this, because our endpoints are going in opposite directions, we can see that we'll eventually hit all of our x values. And same is true for our y values in this case, because on one end of the graph it's going down, 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 and on the other end of the graph it's going up. So our y is going to be y for all real values. All right. In terms of a maximum or a minimum, we would say there's no absolute max or min. But we do have local maximums and local minimums. And what I mean by that is if we looked at like a particular range of the graph, we could see that we have a local maximum or that we have a local minimum. And we'll identify those. Those happen basically at our turning point. So remember, a vertex in a quadratic is basically where the graph makes a turning point. So we're going to say that there are local max or mins at the turning points. And talking about those endpoints again, just remember that it's similar to linear endpoints, right? How a line can slope up to the right or slope down to the right. So when a line is positive, it moves up to the right, and when it's negative, it's going to slope down to the right. All right? So that is kind of a summary of what odd degree polynomials look like, the positive and the negative version. So let's quickly summarize an even degree polynomial function. So remember, those even degrees are quadratic. So when the highest x variable is to a power of 2, and the quartic that we saw. And a quartic was, the highest degree was a power of 4. So think about a quadratic for a minute. When x is approaching a negative infinity, y is going to approach a positive infinity because that endpoint on the left is going up. And the same is true on the other side. As x is approaching a positive infinity, y is approaching a positive infinity. So if you have a quartic or anything of higher degree, it's going to be similar to the graph of y equals x squared, which is a parabola. We should all remember what parabolas look like. Okay. As x approaches a negative infinity, so if we're just talking about a negative even degree, then y is going to approach a negative. So our endpoints are going to point down for both positive and negative x in this case. And this is going to be similar to the graph of y equals, this should be a negative x squared. So when we have a parabola open down. So if we were going to draw a quartic for a positive version, we know that both endpoints are going to point up. So on the left side of the graph, it's pointing up, and on the right side of the graph, it's pointing up. If we're talking about a quartic in particular, a quartic is going to have 3 turning points, so it's going to look kind of like a W, like that. And this would, again, mirror or be similar to a positive quadratic, which we've seen in the past. If we're talking about the negative version of a quartic, again, our endpoints are going to go down on either side. As x is approaching negative infinity or as x is approaching positive infinity, our y values are going to continue to go down, and it's just going to be that W flipped over. Look kind of like letter M. And again, this is going to mirror a parabola that's opening down, very similar to that. So if we look at our domain, again, whether it's even or odd, those endpoints continue on out in either direction on our x's. So our domain is going to be x for all real values. Okay, if we're looking at an even degree polynomial that's positive, we can see that we have some minimums here, right? We're not sure exactly where they are, but our y values or our range can't go any more below those. Our range is going to be from those minimums up. So we'd say that our range for a positive even degree polynomial is going to be y for all real numbers such that y is greater than or equal to the minimum. And obviously the opposite of that would be true. In the case when we have a negative even degree polynomial, we have these maximums here. So in this case, our y is going to be all real numbers such that y is less than or equal to our maximum. So our y's aren't going to go anywhere past those maximums. They're going to be that maximum or anything below it. All right, so is there a maximum or minimum value? Well, yes, obviously, if we have a positive, it's opening up, we're going to have a minimum. If we have a negative and it's opening down, then we're going to have a maximum. And just let's make that point that we did over with our odd degree one. So this, our even degree polynomials will be similar to quadratic endpoints. With quadratic endpoints, either both endpoints are pointed up or both endpoints are pointed down. And we know that if they're positive, it's going to point up, and if it's negative, the endpoints point down. Okay? All right, so let's look at some actual graphs of functions and see if we can determine, is it an even or odd degree polynomial, and is the leading coefficient positive or negative? And we'll refer back to that table to help us. So if we look at graph A, it looks like both endpoints are pointed down. So when we see pointed down, we should start to think that it's negative. Okay, but let's answer both of these. So number one says, is the function even or odd? Well, if we look up at our graph, we can see that when we have both endpoints pointing in the same direction, we have a quartic or a quadratic or something of even nature. So this is an even degree. Is it positive or negative? They're both pointing down. So down equals negative. All right, so it's going to be negative. If we look at B, we have one endpoint going down and one endpoint going up. So that's going to tell me that I have an odd degree one, because if we refer back to our table, we can see that our end behaviors are opposite in behavior, right? When one is negative, one is more positive, okay? And if we think about this in terms of an odd degree and mirroring that of a line, well, we could see that the endpoints are following the same characteristics of a line that slopes up to the right or a line that is positive. Okay, pause the video and see if you can answer for C and D. Okay, so there's the solutions for C and D. Let's just look at a few more examples to discuss further even and odd degree polynomials, as well as if the leading coefficient is positive or negative. Okay, so finally, consider this polynomial function f of x equals x cubed plus 3x squared minus 4x plus 1. Is the polynomial function an odd degree or an even degree? Okay, well, it is a degree of 3. So therefore, it's an odd degree polynomial. Is the leading coefficient positive or negative? Well, my leading coefficient is on my x to the power of 3, and it's a 1, and at that, it's a positive. So we can say it's a positive 1. Describe the end behavior of the polynomial function. So remember, if we have a degree of 3, then we know we have a cubic. Okay, and remember, cubics either go like this, or they go like this. All right, and if we have a positive version, then it's going to mirror that of a positive slope of a line. So we're going to have this first one. So describe the end behavior. So if we have this rough sketch here of a cubic, we can see that as x approaches a negative infinity, y approaches a negative infinity, and as x approaches a positive infinity, y approaches a positive infinity. I just want to do a little bit better of a drawing of that. So if we had a cubic on an x and y axis, if we have a cubic, so a degree of 3, and it's an positive one, it's going to start something like this and dip back down and then go back up. So that down to the left, up to the right. All right, so let's look at a graph and again see if we can pull out kind of all of these characteristics that we've talked about in the notes today. So the degree of the function, okay, we have two endpoints pointing up, which should tell us that they're pointing in the same direction. So we're going to have an even degree at that. Okay, we've seen what a quartic looks like, where we have the 3 turning points, the 1, 2, 3 turning points. So we know that this is a quartic. And we can say a degree of 4. What's the sign of the leading coefficient? Well, like I just said, it's pointed up. So it's positive. The end behavior, again, pointing up. So y is always approaching a positive infinity. So as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y is still approaching a positive infinity. Both are pointing up. If we look at our domain is x for all real numbers. Okay, those arrows are going to continue on going out to the left and right until we get all x values. Our range is going to be y for all real numbers, such that we can see that the graph has some local mins and maxes, which we'll talk about in a minute, but we have an absolute maximum down at the bottom of our graph, right here, right? That's our lowest point on the graph. So that's what we call our absolute maximum, or absolute minimum rather. So we can't have any y values below that. So we're going to say y for all real numbers such that y is greater than or equal to a negative 9. All right, let's look at our maximum and minimums. So we absolutely have an absolute minimum at y equals negative 9. Okay, so let's just draw an arrow to that. But we also have what we talked about earlier are these local maxes and mins. So if I was to highlight, okay, within this range right here of my graph, I do have a minimum that falls in there. Right there I have a local min. So let's write local minimum. And I also have a local maximum. If I wanted to kind of look in this range of my graph, I have a local maximum that occurs here, right at 0, 3. So let's call that a local max. Okay, so I have a local maximum at y equals 3. And then we have a local minimum at y equals -5. All right, so lots of information we covered today. The big takeaway is to understand what is the degree of the function, what is the sign of the leading coefficient on a function, and how do those values determine the end behavior of that function. And that's it for today.